What was 9.2 all about? Let's go. What was 9.2 all about?
Fluid and pressure.
Yeah, fluid and pressure. Very good. So we looked at pressure at a depth in fluid. We looked at Pascal's principle. We looked at a hydraulic lift. Who can tell us what Pascal's principle states? Maybe somebody who did the egg extra credit can describe what they felt.
Oh, that if you put the same amount of pressure, it's spread throughout the whole surface.
Yeah. And doesn't break or it's in equilibrium in a sense. Good, very good. Okay? Fluid pressure in a closed container is equal throughout the entire container's walls. Okay? So what did Pascal's principle enable us to do as a result? Yes, that's the whole thing is hydraulics. Very good, Ev. Without Pascal's principle, it wouldn't make sense, the laws that we use to measure quantities in hydraulics, to perform experiments, to make machines using hydraulics. Okay? The application that we specifically mentioned was a hydraulic lift. And how did that work? What was the formula involved and stuff for hydraulic lift?
F1A1 equals F2A2.
Good. Raise your hand, please.
Equals F2 over A2.
Good. So that is Pascal's principle. F1 over A1 equals F2 over A2. Now, where does that stem from? It stems from P1 equals P2. If Pascal's principle didn't hold, we couldn't write this equation. The pressure has to be the same throughout for this to be true. What was the key to this? What did we get as a result when we used a hydraulic lift? Anybody remember? There was a big thing we wrote at the end, like a conclusion that said, like, this is why it's really important, actually.
Same.
Why was it important? Look at your notes. Look at the example that we did. The mathematical example we did with the hydraulic lift. We made a little comment about it, and we talked about how it's like a pulley, or a wheel, or a ram.
The force applied is a fraction.
Raise your hand. Ev, thank you.
Force applied is a fraction of the force felt.
Yeah, that's the whole key. You only apply a force of maybe 50 newtons, and what do you get out? Like 200 newtons, 500 newtons, something much bigger. So you have a mechanical advantage. The whole key here is that we're able to create a mechanical advantage using a hydraulic lift. All right? So let's say I put in 500 newtons, but I get out 1,000 newtons. What's the mechanical advantage? It's a ratio.
5, 2 to 1. 5 to
I put in 500 newtons.
500.
I get out 1,000 newtons. What's 1,000 over 500?
5.
So there, 2 to 1. Mechanical advantage would be 2. If you put in 500, you get out 1,000, you doubled, didn't you?
Yeah.
Put in 500, you get out 1,500, you've tripled. Put in 500, you get out 2,000, you've quadrupled. The amount that your factor of increase is the mechanical advantage. Is that clear? Again, the force felt by the car over the force applied is the mechanical advantage. Now, again, this stems from Pascal's principle, which says P1 equals P2. The original formula, though, we should not forget, for P is P equals force over area. What does this tell me? Give me some sort of a statement based on this. What can you say based on that formula in the top right?
Force equals the pressure times.
Okay, you can rearrange it and say the force felt is the pressure times the area. That is true.
The more area, the less pressure.
That's it. Very good. The more area of contact, the less pressure. That's why if I go up to a balloon and I go like this and smack a balloon, it doesn't pop, does it? But I can just go up and put a little bit of force with a needle and what happens? It pops. Because it's such a small area, the pressure goes up so much when you poke it with a needle. It's like when I was giving the demo in the front, I just simply said, I'm standing on my feet, on my 2 feet. The area is the area of 2 shoes. The minute I do this, what am I doing?
1 shoe.
Yeah, so it's half the area. If I halve the area, I double the pressure. They're inversely related to one another. Okay? Inversely related. Have you ever seen somebody or ever gotten acupuncture or somebody that acupuncture might not be good, but they lay on a bed of nails? It's another really good example. Yeah, it's a bed of nails, so you think it would hurt, but if there's a nail in every so odd location, there's enough area to displace the force of your body. So if you lay on one nail, what happens? It hurts. It goes into your back, obviously. I mean, unless you're Superman, obviously, right? Maybe like Joyce. Right? So here's our formula for pressure. Here's Pascal's principle. All right? We applied that to hydraulic lifts. Was there anything else in section 9.2 we should be concerned with? What about the pressure and depth?
Yeah.
Wasn't that in there? Let's write that down. Okay, that's our formula on the right-hand side. What does capital P stand for by itself? Not P0, just the capital P. But what should you say? Not just pressure, but the...
Pressure felt. Absolute pressure.
Either absolute or total. Very good. Okay, absolute or total pressure here. This is the overall pressure felt. What is P0 though?
Solid.
Atmospheric pressure. What is rho GH the pressure from? What is rho GH the pressure from? Nick? The fluid, what fluid?
The water.
Yeah, usually the water. Good, Nick. Not the fluid that we're in now. The fluid that we're in now exerts pressure on us. That's P0. But if now we're underwater, it's like the air is pushing down on the water, and the water is pushing down on us. So we feel both, don't we? So we feel the sum of these two pressures when you're underwater. Okay, it's like stacking two boxes. The table feels the weight of this DVD case, right? But now it feels the weight of the DVD and the remote in that same spot. You add them together as vectors pushing down. So the pressure pushing down in the atmosphere plus the pressure pushing down from the fluid that you are submerged in. Focus, focus, focus. Come on. Correct. The fluid that you're submerged in. That comes from the rho GH. What does rho stand for? What is G? And H? Depth, really. Okay, but you could say height. The height of the column of water on top of it. That's
Density of the water, right? Or whatever it's in.
of the fluid, rho F. I'm not getting that. The density of the fluid.
Can you explain the example we did in class with the flashlight with a box of water?
Yes, that's exactly the one. Yep. You shine it up, you see a column of water. That column of water, the weight of it is rho GH. RHO. Okay. All right. 9.3. 9.3.
Scholars talk about with column of water, we need to measure the volume of that column.
No, we use that to come up with the equation. Once you have that equation we just used, all you need to know is the depth. That's it. If you know the depth of the object, you know the density, you know gravity, just multiply them, add P0. If you wanted to derive it, you would have to use that. Stop. If you wanted to derive it, you would have to use that, yeah. All right, 9.3. What was 9.3 about?
Fluids in motion.
Yeah, fluids that are moving now. So water flowing through pipes. Okay, in your house, a radiation system. Mike, I'm serious. Focus. You're not helping us if you're not focused. Water flowing through the pipes in a house, the laws that they follow, the continuity equation. Okay, the continuity equation told us this. The area times the velocity is constant no matter where you are in a piping system. And that is what allows us to say that when you take your thumb and put it over the end of a garden hose, the velocity increases a lot because you're decreasing the area. They are inversely related. Okay, they're inversely related. Now, one thing that people confuse still, and I explained this in the other class, and they were like, oh, the volume coming out is still constant. The amount of volume that's coming out is still constant. So, for example, I'm outside in the backyard and I've got a 5-gallon bucket, and I need to fill up 2 of them. And I happen to have 2 ends of a hose. The same source, but 2 ends of it. One of them, I just put the hose in. The other one, I put my thumb over the end. And it shoots out much faster into the bucket. Which one fills first?
The same.
What?
Why the same?
No, the first one goes up.
No, the second one.
The one that
Wait,
you
you just
You just said it came out faster, so obviously.
This hose is just being held over the bucket of water. Same exact spigot. Same amount of volume moving. This one, I put my thumb over the end of it. And it comes out faster, like the velocity increases a lot, right?
Same.
So I'm putting them out there. Which one fills up first?
Same.
The one with the
That was a trick question. I think it's a trick question.
The
One
one
what you did.
Neither of them fill
There's a
up,
hole in
the
the
buckets are
bucket.
big.
At the same time.
Because the
It's the
It's
one.
the same.
No,
Let me explain.
right.
People think it's the one with your thumb over it because the velocity increases, but it's a smaller cross-sectional area. So at the end of the day, you still have the same A times V gives you a volume, guys. Area times velocity ends up giving us a volume here. Okay, so in this case, well, volumetric flow rate, really. It's the same amount of fluid still flowing out. How, follow-up question, how do you adjust the amount of fluid flowing out? Not the velocity. Again, you can adjust the velocity by putting your thumb on the end. How do you adjust the amount of fluid flowing out? No, that's the velocity.
Take your thumb off.
If you move that, it's the velocity.
Take your thumb off.
It has to do with the volume, but I'm saying physically, how do you control
Add
the
salt.
volumetric flow rate,
Add
the
salt.
amount?
Add salt.
You turn
No
the
salt.
wheelie thing.
What is it, Mike?
Maybe.
You turn the wheelie thing.
Yeah, you turn the knob on the spigot. There's a valve. There's a valve. You turn that little valve, right? It opens up a gate valve or it moves back a ball valve, either one. Fluid flows through. If you open up the gate valve all the way, more fluid is allowed to go through, actually. Now, once it's in the pipe, though, you can use your thumb to control the actual velocity at the end. Okay? So the continuity equation told us that the products are always equal to one another of A, V, at any point in the pipe. So I could have a pipe that looks like this. Ready? Varying cross-sectional area. Okay, so I have a medium cross-section, a small one, and then a large cross-section. Either of these cases have different areas, so they'll all have different velocities. But there will still be the same amount of volume flowing in the pipe. Okay, it will still have the same amount of water flowing in a given time period. You can prove this mathematically. What's the units of area?
Meter squared. Meter squared.
Let's say meter squared. What's the unit of velocity? So you get meters cubed per second. Volume moving through the pipe every second. This is a volumetric flow rate. A good word to know. Volumetric flow rate. Cubic meters per second. Volumetric flow rate.
That's the units.
The units turn out to be meters squared times meters per second, which is meters cubed per second.
Your hands are.
All right, that was the continuity equation. What else?
Do the pressure from the pipe. Like the smaller pipe has less pressure than the larger one.
Yeah, well, what did that come about from? What principle? Bernoulli's. Bernoulli's principle tells us that as the velocity increases in the fluid, the pressure decreases, right? Pressure decreases. So we looked at the example of a bottleneck function. Imagine traffic is flowing, right? Here's traffic coming in 4 lanes, and then suddenly there's only 2 lanes in the traffic. Everything backs up, doesn't it? So there's high pressure here. There's low velocity here. But then once you make it through the bottleneck, you start to coast, right? Cars start to move actually, because now you're actually moving in flow. So velocity increases a lot. Pressure decreases here.
Do you ever fold a piece of paper and like blow it between a piece of paper?
No. Is it cool?
Like it's the principle. Like.
Wait, what was it at?
Okay, go ahead. So fold it like this?
Fold it.
Oh, literally fold it
Yeah,
like crease
make
it?
it thinner. Like rip a piece off.
Rip it this way?
Like.
Just do it. I don't know if we need that though. Do we need it? We don't. They're done. You're good. You're good.
Are you sure?
Is there a name on it?
No.
I'm watching.
Anybody? Yeah, give me a piece of paper that we don't care about. That's fine. We'll live.
And then you blow in between it, because they go together. They don't go apart. Because
Oh, yeah, absolutely. Okay, so what I was saying is you would think that when you blow through this that it would separate, right? The two of them actually come together because of Bernoulli's principle. Was that in your textbook? It was something about like, I think it was water flow or something where it pulls it one way versus the other because of the pressure differential. I'll look that up, but I do remember reading something about that in your textbook. Yeah. What did this enable us to theorize or come up with as a result of Bernoulli's principle? It's a big discovery.
Airplane wings. Oh, okay.
Yeah, airplane wings and lift and drag. So let's draw an airplane.
Oh, that's what we used to be at.
That's a terrible airplane.
It's a wonderful airplane.
Looks like a whale.
So this airplane that's cruising, do whales have windows in the front of it? I mean, come on, it's clearly an airplane.
Really?
Look, it even happens to say JetBlue on it. What whales say JetBlue?
That doesn't look like a jet.
Anyway, so here's what happens. Here's what happens. Shh. Listen. The air flows faster on the top of the airfoil or the wing. The air flows faster on the top, creating a lower pressure on the top. The air flows slower on the bottom, creating a higher pressure on the bottom. If there's more pressure on the bottom than there is on the top, you have what's called lift, a force of lift directed upward on the plane. As a result, the lift overcomes the drag and the plane lifts off.
Wait,
Yes.
why is
How do you write
Bernoulli.
Hey, that's my son.
Bernoulli. LLI.
Say it again.
Bernoulli.
Wouldn't the pressure on the top be bigger?
The velocity on the top is larger. It has to do with the shape of the airfoil. They're shaped in a certain way so that the air streamlines.
Wouldn't it be greater here because it wouldn't?
The velocity is greater on the top.
Oh, that's what I'm thinking.
Pressure is lower.
Oh, okay.
Okay?
What if it's the other way around, but just not lift it up?
Yeah, what? Just stay on the ground.
We didn't notice that, or we just.
Well, that's what happens, guys. When a plane wants to land, what do you think happens? It changes the angle or the pitch of the flaps. When it changes the flaps, it decreases that lift. It decreases. You okay?
Yeah.
It decreases that lift. It decreases that lift, and increases the drag, causing the plane to start to descend toward the ground. That's what it's the inverse of this, or the opposite. What was 10-1? Easy section, easiest one of all.
Temperature.
Temperature scales. Okay? Two basic ones are Celsius, Fahrenheit. And the others are Kelvins and Rankins. Now, raising your hand and answer this, please. What is the use for Rankine and Kelvin? And describe the idea behind it.
Say again?
Rankine and Kelvin, what's their importance?
Kelvin.
Raise your hand, I said, for this one, please. Smitty,
Those are something like they can never be negative.
why? They're absolute temperature scales, thus they can never be negative. This is Kelvin and Rankine scales. The lowest temperature they can be on the scale is 0. Why is that? What's the whole idea behind it?
It's like the kinetic energy of the particles, so it can't be zero, because there's no way to stop it.
So the absolute temperature scale, 0 indicates absence of any thermal motion whatsoever. Now, what Elliot is talking about is the fact that, Mike, pick that up, please, is the fact that it's asymptotic to that. So you can get close to 0, but you can never get there. Reasoning, Elliot said there's two reasons. One, logic, things always have some energy. And two, what was the other reason? There's one other reason, Scott.
You need something colder than it to make it that.
Exactly right. How do you cool down a bottle of soda? You put it in the fridge. The fridge is colder than the soda. It takes away the heat. It gets colder. So if you want to get to 0, you would need something colder than 0. But absolute 0 is the coldest you have. So there's no fridge that's colder than 0 to make it 0. So physically speaking, you can never get to 0 kelvins or 0 Rankins. It's a limit. It's a limiting function. You know asymptotes from math, you get closer and closer to the asymptote, but you never get there. Okay, that's a really good example of it. It's like, have you done the example if you walk halfway to the wall? So simple. It's a good example of a limit or an asymptote. Walk halfway to the wall. Okay, I'm here, right? Now walk halfway to the wall. I'm here. Now walk halfway. It's about half. Now half. Will I ever really get there? Sure, but theoretically, no. Keep having something. You never get to 0. Divide anything by 2. You keep getting a smaller, smaller, smaller fraction. You never get to 0. Same idea as this. You can never get to 0 Kelvin because you have nothing smaller than it. So it behaves the same way as the demo I just gave you there. It's asymptotic in nature. You can never get to 0.
And that's true about Kelvin and Rankine.
Say again?
That's true about Kelvin and
Yes, Kelvin and Rankine are both absolute scales. Kelvins are measured in kelvins. The Rankine scale are measured in degrees Rankine. Rankine is associated with Fahrenheit. So if you need a Rankine temperature, you better know the Fahrenheit. If you need a Kelvin, you need to know the Celsius. You have 4 formulas there on your formula sheet. Loaded from Moodle so you're familiar with it. Please don't ask questions of what formulas are on there. You have it on Moodle. Anything else on 10.1? Did we talk about anything else in 10.1? I'm trying to think back. Look at your notes real quick. Was there anything that was like, oh, I don't know what that means?
Equilibrium?
Was that in 10.1 or 10.2?
That wasn't 10.
It wasn't 10.1?
That's temperature and thermal equilibrium.
Relate temperature, kinetic energy.
Okay, I'm trying to think of what I talked about in that section with it. We'll wait till 10.2 because we're going to talk about in 10.2 anyway, with equilibrium. Oh, yeah.
So we should memorize the equations for the temperatures.
Are they there?
Look at the formula sheet.
I don't see them.
Did you go to the new one on Moodle?
You made a brand new one.
I just made one, I said, yeah.
Okay. Once you clean up the wax out of the ears, they all shit.
Oh, buddy.
Yes. You have new formula sheets courtesy of Smitty and Julia, who came by to laminate them the other day.
Julia.
Okay. Julia, Arcia, and Smitty came by after school to laminate the...
Oh,
Julie.
because you call her Julia?
Did I say Julia?
Yeah, it's Julia.
Oh, I meant Julie. Her real name is Julia.
Yeah,
But I meant Julia. Anyway, let's move on to 10.2. It was 10.2/10.4. What was the whole idea behind 10.2?
Swag.
Physics.
It was not swag, no. What was the whole idea behind 10.2 and 10.4? Heat, transfer, and controlling it. So the modes, yes, and the modes are useful. So, before we start, what is heat defined as and how does heat transfer work? What is heat really and how does heat transfer work?
Transfers work with
Okay, so the kinetic energy of the material is different in two spots. So, I apply a heat source to this part of the table, so it's really hot right here. It's cooler over here though. What will happen is that heat will want to come to equilibrium, want to spread out. So the molecules over here are vibrating faster. They have a higher kinetic energy because they have a higher temperature. The molecules then cause the molecules next to them to vibrate, causing the next ones to vibrate, and that vibration gets propagated throughout the table. Eventually, over time, hopefully the whole thing will come to thermal equilibrium. Now, unless you're generating a constant heat source, that won't happen. Right? If you're constantly generating a heat source, it's not going to come to equilibrium. But if you heated this up and then moved away and released it, it'll be hot for a few seconds, but eventually what will happen? It'll cool back off. That heat transfers. It goes from hot always to cold. So the vibrations dissipate. The vibrations become minimal here, and the vibrations over here increase, so the temperatures go from really high temperature and really low to somewhere in the middle. That's the whole concept behind heat transfer. You need a temperature differential. All goes back to that always. It could be two objects separately. It could be one object with one part that's hot, one part that's cold, and it just wants to spread throughout it. Okay, we talked about modes. We'll talk about it in a minute. And modes are a different thing. Trying to think if there's something else in the beginning of this
Wait,
section.
so heat transfer was goes from hot to cold?
Always from hot to cold. Yeah.
You did heat and work too.
Oh, good. Heat and work. Thanks. Heat and work. What's the relationship between heat and work? Yeah, Nick, go for it.
If you're doing work on an object, you're changing the internal energy, so it's basically changing the temperature.
Yeah, exactly right. So if you do work on an object, and we knew this from the work kinetic energy theorem, right? If there's no friction involved, then yeah, nothing's going to happen. But in real life, there is. That's what Nick's describing. So Nick's saying, for example, like the one we did, I think we said a nail, right, in class? Was that what we said in this class or the other class?
The eraser when you erase.
Oh, eraser was another one, yeah. Or a paper clip, or a rubber band, yeah. When you do work, you're changing the molecular structure. You're stretching out those bonds. You're causing it to increase in internal energy and thus increase its temperature. Okay? Let's go to the modes. Let's go to the modes. Can I get a hand to see what the modes are of heat transfer? There were 3 of them, Catherine.
Conduction, convection, and radiation.
Conduction, convection, radiation. Very good. Let's talk about each of them and let's talk about some of their applications. Conduction. What do you got? Conduction. What's the whole concept behind conduction and thermal conductivity? Scott.
Conduction was one. There was like the table where you put your hand on it and it disperses because there's a difference in temperature.
Yes, that's exactly right. And it's due to contact. So I put my hand on the table, the hand is warm, it's warming up the table right now because there's a difference in temperatures. Conduction always refers to things in contact. You don't realize that though. An application of this that we talk about for insulation is using air between two panes of window glass. Air acts as an insulator. It has a very low K value. Its thermal conductivity is very low. Its K value is low for air. For metal, the K value is high. So because the air's K value is low, it acts as an insulator. So here's what happens. Ready? You've got your glass, you've got your air, and then you've got your other glass pane. The heat in your house is trapped here. It could easily make it through this glass. Ever touch your glass window on your windshield or your window in the winter? Isn't it really cold?
Yeah.
Glass conducts heat, cold and heat in general very, very easily. So the heat travels through this and gets out of your room. But then what's here? What did I say is here in between? Yeah, air or argon or some sort of gas, right? That gas acts as a thermal barrier. It keeps the heat trapped in. Okay, it keeps the heat trapped in.
Can you do the reverse? You know when you leave your car out in the sun for like a while, it gets hot, like really hot?
Yeah.
Could you do the same with that?
Yeah, absolutely. The glass would be really, really hot. Absolutely. It'd be the opposite of it. But because of the fact that its K value is significant. Okay? Remember, the K value represents the thermal conductivity. Thermal conductivity. Application for a computer. How did this work? What was this one we looked at?
Heat sink.
It's very simple. What was it called?
It's a heat sink.
A heat sink. Nick, explain how a heat sink works for us.
Your CPUs are under solid aggregates like heat, so you put a piece of metal of a high like heat conductivity under the CPU, then you have like a cooling system, like tubes of coolant moving around the heat sink or a fan to cool it down.
That's exactly right. Okay, so he went into conduction and into convection also. We'll talk about in a moment. The conductivity part is the heat sink being touched to the CPU. The CPU dissipates its heat. The heat sink absorbs it. That's why it's called a sink. A sink means it absorbs. A source means it gives out. Why do you think it's called a sink? All the water is going to one location. A heat sink means it's taking all the heat. Okay? So the heat sink acts to draw in all that energy. Then, as a result, afterward we use convection to cool it off. Let's talk about convection now before we get to the computer part. Convection. We got. What's convection? Convection. Elliot.
It's like the way the particles move in a fluid when it's like when there's a heat transfer.
So it's fluid motion, good, and causing heat transfer. So if you heat up the bottom of, or you heat up a tea kettle, the bottom of the water gets hot first, right? Because it's directly connected or contacted to that metal lining, which is getting heated up from the flames. So the hot water, what happens to it? It starts to rise up. It's less dense. Cold water falls, and you get this convective current. Okay, convective currents. It's how a convection oven works as well. It's how really an air conditioner works as well too. Okay. Now, in a computer, what Nick was mentioning was the fact that when the heat sink absorbs all the heat, it's got to go somewhere. So a fan runs over the surface and cools it off. Or you run tubes of like something like liquid nitrogen over it that doesn't heat up very quickly and can absorb most of that heat. Okay, it cools it down. Cools it down. That's convection. Convection involves, remember, the buoyancy of the fluid,
Pressure and temperature.
the pressure, and the temperature. The thing that you look at is H for this. Remember little h? It's the convective coefficient of a material. What do you want to have a lot of for convection? To reduce the heat, a lot of something. Metal, sure, is a material.
Is it like the heat or like the
Yeah, so you increase the what when you make fins?
the surface area.
Surface area, good. So the more fins you have on a radiator,
Oh.
the more area is exposed, the more convective currents can flow across that area and release the heat into the room. So the higher the area, the higher the heat transfer due to convection. The higher the H value, the higher the transfer due to convection. Radiation, finally. Radiation. The one that's different than the other two, no matter is involved at all. No matter.
Oh, it's like the sun.
Yeah, it's like the sun.
The waves of the sun.
Okay.
How is this
I
different
like
from radiation
heat
for
through
chemo?
space.
It's a different wavelength that you're receiving. Maria, go ahead.
It's like the heat that travels in like space. Like
Yeah, it's the heat that travels as a result of some electromagnetic wave. Okay, the heat that comes from an electromagnetic wave. You can get like radio waves and gamma rays and stuff like that, or different waves that are not really heat producing. This is a specific type we're talking about, radiation that involves heat.
Okay.
There's other radiation, obviously,
Yeah.
okay, like radioactive decay and stuff, but this is a radiation involved in heat specifically. What portion of the spectrum are we looking at usually here?
Infrared.
Yeah, infrared for human beings that give off certain wavelengths. Okay? But the idea is that you're giving off a wavelength to lower your internal temperature. Right now, bless you. What's the temperature in the room? Ish.
68.
70 degrees maybe, let's say, room temperature. What's my body temperature and yours?
98.
So which is higher? Yours. So there's got to be heat transfer, right? You're radiating energy. You're radiating heat. Okay? It's lowering your internal temperature, but you have constantly being generated heat at the same time. You are not only giving off heat, but you're a source of heat. That's why you huddle close when you're cold with somebody, keep body heat. You get people around you, it acts like like a little space heater in a sense. Okay? Anything else in this section? I think that was it, right? In 10.2, 10.4? Let's move on, 10.3. We're almost done, we got about 7 minutes. Oh no, oh yeah, not even, right? What is it? It's examined. So we've got 5 minutes, let's quickly go.
10-3.
Okay, the first one is used when you increase the temperature of a substance but do not go through a phase change. The second one is used when you go through a phase change. The third one is just our conservation of energy that tells us that we can set two things equal and find the specific heat of an unknown substance. That was calorimetry. Okay? So if we have water going from 40 degrees Celsius to steam at 120 degrees Celsius, how would I go about solving a problem to figure out how much heat is involved in that process, Maria? Maria had her hand up, I thought. No? Camille?
Okay, so from 40 to 100,
Okay, it is what?
temperature change.
Good. So that's Q1, right? And this is going to be MC delta T for Q1. What would Q2 be then?
Then Q2 would be wait, it would be from 100 to 140. That would be a phase change and a temperature.
Alright, so we have to separate them though.
Yeah.
So phase change goes here,
And then
and then temperature change goes here. Alright? So again, this is the C value for Q1 for water. This is the C value at the bottom for steam. Delta T would be 100 minus 40, the temperature change while it's still water. And then if what did I say, 130, we go up to 130 degrees? 120? 140. So if we go up to 140 degrees, this would be 140 minus 100, the temperature change while it's steam or gas. Is there no temperature change here? Why? Phil?
Well, in that equation, there's no temperature change because you're looking for the energy from when you're changing the phases.
Exactly. It's not a temperature change, it's a phase change. So we're saying, you know what? We have the mass and we multiply by the latent heat of vaporization for water, given in your tables. The two tables in those notes there will both be on the test. Okay? Both tables. So you have to find each part. Now, from this, we were able to say Q1 equals Q2. Let's go back to that. If I have an unknown substance, like a sword,
Well, do we usually do the math on this?
are we going to do the math behind this part right here? No. Theory. I didn't go into the math. We ran out of time. Math is pretty easy though. So the sword is really hot. Okay, we want to cool it down. Let's make believe that when you put the sword in, it's not going to produce any steam. Because the minute it produces steam, now you have a phase change also, which messes things up. So let's say you put the sword in, it cools off in the water, and the water temperature just goes up. Now, all of the heat is trapped in a system here. We assume that this is all in an enclosed system where no heat can be resolved or released. So the heat given up by the sword all goes into the water. So we could say, as a result, let me put this over here. As a result, we could say, come on, there we go. M1 C1 delta T1 equals M2 C2 delta T2. Let's say that the sword is the second object and the water is the first object. Okay? We know the mass of the water. How come? We just measure it. So we've got that. We know the specific heat of the water. If you want to know, by the way, how to find the specific heat of water, I said this already in this class, right? I put up a video on News Forum that resent.
No.
You sent me a video, didn't you?
Send it, but you didn't talk. No, it was an article.
Article, not a video. But there's an article in there on News Forum, okay, that discusses how to find the specific heat of water. Remember that question we posed? If we use water to find other things, how do you find water, kind of? It's very actually simple using electrical current. So then we look at the change of temperature of the water, which can be measured with a thermometer. So all of these factors are known. The mass of the sword can be measured. The temperature change of the sword can also be measured. So what's the only thing we don't know? Okay, C2. So as a result, the mathematics behind this is actually quite simple, whoever asked that question. Just rearrange it, solve for C2. Plug in the mass of the water, specific heat of the water, change the temperature of the water. Divide that by the product of the mass of the sword times the change in temperature of the sword. That will give you the specific heat of the sword. Okay?
Why is it all bloody?
It's not. It's hot, so it's red. It's a hot. You know when you like the metal workers, what are they called? Blacksmiths?
Yeah, you're just sick.
No, they used to heat up the sword. It would be like red, emanating heat. One thing I didn't mention: laminar versus turbulent flow. That was in section 9.2 we talked about. Okay, what is laminar versus turbulent flow? What's the whole idea there, Nick?
Laminar is like smooth flow alternative to choppy kind of.
And what number did we use to measure? We talked about. We didn't actually calculate it. It had a certain name. It's used in engineering. I mentioned before.
Oh, the little squigglies, it's approximately, right?
No, it was spelled with a capital R, E,
Rankin's number or something.
Y.
Reynolds number.
There it is. Reynolds number.
You know.
Reynolds number. We didn't go into the math behind this, but you should know the theory. If it's above a certain value, the flow is turbulent. If it's below it, it is laminar. The values that enable you to calculate Reynolds number: velocity, density, viscosity. That's like the thickness, like syrup versus water. So velocity, density, viscosity, and the diameter of the pipe. Okay? A lot of material. Make sure you study. There's no problem set, so look at your notes, look at your examples, look at your homework.